organizers for inviting me, and because as I've seen this conference is meant to promote young people, I really wanted to highlight from my collaborators here, the young ones. And unfortunately, they're not here, but hopefully you guys will meet them at various conferences. So in particular, so this is some work I've done with Arthur Lipstein and Ricardo Monteiro, but the young collaborators are Kyuya Liang, Chandra Chowdhury, and Kajal Singh, and they're from slightly different fields. So they're like from cosmology, correlators, asymptotic symmetries, but they're all really excellent. So I wanted to promote it. Good. So having said that, I'll jump straight into it. And the first half of the talk or so will be on finding a toy model for gravity, but when we work on curved background. So in particular, I will focus on some very simple ones today. So de Sitter or anti-de Sitter, which for the purpose of what I'm doing, you can always jump between the two. And I'm imagining doing some kind of perturbation theory to whatever order we want to on these backgrounds. Now, the main thing is that almost everything that you want to compute on a curved background is much, much harder than on a flat background, right? So instead of amplitudes, you've got these correlators, which are much, much harder, and we're far behind in the program of computing these. Even things like soft limits and asymptotic symmetries are a lot harder to find. Things like the double copy, there's not really any agreement, I would say, on what exactly should be on these specific backgrounds. And so this is why we wanted to first find a toy model in which to look at these questions. Okay, so what is this toy model? It's just the self-dual sector. And this is something that you should have seen, hopefully, those working in particles, in flat space. So I'm going to start with the definition of this just in flat space. And I'm going to give you two definitions. Depending on your background, you might prefer one of them or the other. So first, for the amplitude sort of people, you know that we have the helicities for the gauge field and graviton, plus and minus 1. And then we have these scattering processes. And then the self-dual sector is simply the statement that I throw away half of them. So then all my processes, so say, let me throw all the negative helicity, so I only look at processes like this. Now, something nice about this self-dual sector is that it's not just a toy model. So once I do this, so first let me say, once I do this, the theory becomes much simpler, right? So in particular, it's integrable, everything is very easy, so I can ask a lot of questions, and I'll show you some examples later that are just much easier to answer. However, it's a bit more than that. So I can actually go there. There's a way. So in amplitudes, people will be familiar with things like MHV and MHV. So there's a way of going away. So first, let's look at the right-hand side of this. From the toy model here, so the self-dual. So what I'm saying here, so I have some particles here. I'm counting particles. In the self-dual case, let's say I have none with negative helicity and they're all with positive. There's a way of slowly introducing one by one the opposite helicity and doing computation in that sense until I get to the full theory where I have some arbitrary numbers of each. So I guess what I'm saying, there's an alternative perturbation theory that's different from the maybe more standard one that we're used to, which is in coupling constants. Good. So the second definition, which will actually be as a starting point, will actually be more useful for generalizing to curved backgrounds, is the field one. So this one, again, I'm doing it here for gauge theory and gravity. So at the level of the field strength for the gauge field, I'm just taking the dual, equating it to itself again. For gravity, I'm taking the Riemann tensor, I dualize over the first two indices here, and I equate again. And it can be shown that the two definitions are completely equivalent. Good. Any questions? So this was all in flat space until now. So now we want to take this and generalize to, well, we did it specifically for ADS. So this is kind of the simplest sort of non-trivial, interesting background that you can have. So for ADS, we actually, I'll show you this quickly because it turns out that it ends up being identical to flat space for Yang-Mills. So we found that it's useful to work with this specific metric in the Poincaré patch. This is the self-duality condition now, so you just have the root G playing a role here. And due to the conformal flatness, it reduces back to the flat equation. So basically what I'm saying is that this factor 1 over z squared in front, which will appear in your root g, cancels with the inverses of g that I use here to raise the index. So the equation will end up looking exactly like the flat one. So, but I want to show you anyway what it looks like, because it turns out that it acquires a very nice and simple form. And in order to do this, we work in these light cone coordinates, and then we just rewrite the metric in these light cone coordinates. Good. So
Their I was really the imaginary unit.
yes, this is really imaginary. Good. So this is something about the self-dual. So here you often complexify your coordinates when you go to self-dual. So here we're actually working in Euclidean ADS. So you see I've got i's everywhere, but you can also do Lorentzian and then you complexify two of them. So we allow ourselves this freedom if we want to. Good. So something very nice happens. So remember I was telling you before at the level of helicities, I've thrown away one of my helicities. So from two physical degrees of freedom, I'm left with only one. And this is really reflected in the way that you can write your field. So if I have some field satisfying this condition and I go to light cone gauge, it turns out, so I impose this, it turns out that this guy also vanishes and these two can be written as just derivatives of some scalar. This is all very nice. And then the dynamics, all the dynamics of the theory is just encoded in this equation here. Now, it turns out this is some work that the Donald and Ricardo did some years ago now. Some very nice things happen here. If you split your spacetime into two planes, I'm going to define these operators here. So you might think it's a little bit overkill at this stage because I just have some derivatives. But you'll see later when we generalize to gravity, it's useful to have a little bit more notation. So I've just defined this differential operator here in terms of which these components can be written like this. And then it turns out that you can define this Poisson bracket just like this. So this is from the old paper of Donald and Ricardo. And they've shown, so I think I don't have time to do an introduction of this, but I think yesterday someone talked about BCJ duality and how in gauge theory, we expect to have an additional symmetry algebra because of how we can rearrange our amplitudes. Now, in this simple toy model, it was found that actually you can really make this explicit at the mathematical level in the sense that you can really find a bracket for that algebra. And that bracket is exactly this Poisson bracket here. And I wrote it also with these pi's, but this is for later use. So that finally, we can write this kind of very suggestive equation for the scalar where I'm combining the commutator from Young-Mills and then this Poisson bracket here. Good, so this is kind of both scalar and ADS, self-dual Young-Mills. Now let's go to gravity, because this is where things get a bit more subtle. And here, we will not have the same thing, because now, of course, the metric is part of all of this here. So our first question, because these notions of helicity are a lot more hazy when we're not in flat backgrounds, our first question was how to generalize the self-duality condition itself. So we sort of took the physical meaning of the self-duality equation. So kind of the message coming from the self-duality equation, if you contract two of its indices here, you see that it equates equations with Bianchi identities, which is sort of what you expect, because duality mixes them and then self-duality equates them. So this was our starting point for generalizing. Good, so this was the flat thing. And then in a curve background, which for us, now let's assume any background that has a cosmological constant, we said, let us introduce this tensor. So instead of working with R, let me work with this tensor T, and let me define the self-duality relation instead of the Riemann tensor in terms of this tensor T. Now let's first check what I was showing on the previous slide. If I contract two indices here, indeed, it gives me an equation between the Einstein equation with a cosmological constant on the left-hand side here and the Bianchi identity on the right-hand side here. So it passes the first test of being something that is self-dual, but now in a more complicated background where I have a cosmological constant. Good, but to convince you a little bit more that this is the right thing to look at, recall the relation between the Riemann tensor and the Weil tensor, which is sort of, this is like first course in GR level stuff, is that if I, in flat space, of course, on the support of the equation of motion, they become equal. In curved space, our tensor T, on the support of the equations of motion, the tensor T that we've introduced here becomes exactly the Weil tensor. And for those who are used to working in a sort of spinorial representation of GR, you know that it's the Weil tensor really that contains the helicities. So it kind of makes sense that this is the object that we should be focusing on if we're doing so. Good. Okay, so this was the definition. Now we want to, so remember for Young-Mills, we had a very nice scalar description reflecting the fact that it was only 1 degree of freedom. Now we want to do the same here, but let me first, because I haven't shown you the gravity. So recall again, this was our notation, how we split the planes. We define this differential operator. Now, in flat space, it turns out that, again, because I have just 1 degree of freedom, if I work in light cone gauge again, where I set my h, u, mu to 0, it's all really, really nice. So all the components of my graviton can be written just in terms of a scalar here. Oh, and I wanted to emphasize that here, I'm not doing, even though I wrote an h here, this is an exact h. So this is g minus the background. It's not linearized, it's not truncated in any way. So the full metric minus the background eta can be written in terms of the scalar. And then the scalar satisfies this equation. So now, again, this may look a bit mathematically dodgy the way I wrote the double Poisson bracket here, but I'm just trying to be suggestive. So the way this is defined is that a Poisson bracket, and then the entries are connected like this. So it's as if you act, so remember where I defined it here. This is kind of the definition of the Poisson bracket. So imagine you're acting again with this operation that gives you the Poisson bracket here. Good. So here again, this was a very nice observation by Donald and collaborators that you really see the double copy happening really nicely at the level of these equations. So I'm replacing this commutator. So this is why I like this notation. Good. But now let's go to ADS. And now finally you see why I introduced all this additional notation here that looked a bit redundant, is because now I can define some new pi's. So these were my pi's in flat space, just some derivatives, but notice with different indices. And now my pi tildes are very minimally deformed relative to the flat ones. So I just have a partial W and partial U. So it's basically just this factor, which is the square root of the factor in the metric. Good. So this is our metric now. We write it exactly the same. So again, this is the full metric where I have a background part and an h mu nu part. And then it turns out that you can again write your metric in terms of this 1 degree of freedom. And it works very nicely. So something that surprised us a bit. So in flat space, it has this symmetric kind of quality to it. So it's just a pi acting twice. So we expected there'll be some deformed operator now acting twice, but there's an asymmetry that seems to occur in ADS, and we don't fully understand it, but we think it's because of the fact that we have a boundary in one of the coordinates. So the space itself is not fully symmetric like flat space. It turns out that the way you construct things is as a symmetrized product of these two different operators, where pi tilde is this deformed one here, and pi is the old one from flat space. And then we have dynamics as well, of course, and the dynamics are governed again by this equation for phi that I have here, which is slightly modified now relative to the flat space one. So you see I have the box now is the ADS box. The scalar has a mass which is -2, which is just corresponds to conformally coupled scalar. And then I have again this double bracket. But like I was saying before with the asymmetry, I have this mixed double bracket here. So recall here I was defining this in flat space, this double bracket like this. Well, I was writing it here like this. Now, it's exactly the same, but in terms of this Poisson star that I'll explain on the next slide. So it kind of very closely follows the flat space story, but let me show you what this modified Poisson bracket is. So just to kind of remind you, these were the definitions of the operators, and then the modified Poisson bracket. Yet again, like everything in this theory, for some reason, is a mixing of the pi's and of the modified pi tildes. So you see the definition looks very similar to the flat one. In fact, you can take the flat space limit by taking pi tilde to pi, and it just collapses back to this. So you just define it by the way, the metric was defined by mixing the two. Poisson bracket is again defined by mixing the two. And the crucial thing, again, as with the standard Poisson one, is that it satisfies Jacobi. So it corresponds to an algebra, to an actual Lie algebra in the theory that, well, we say is the kinematic algebra, but now in an ADS background. What exactly it is, so in flat space, there was a nice description of, it was the area preserving diffeomorphisms in one of these planes. We don't have such a nice sentence yet to put on this modified Poisson. We think there's some with twistors, we think there's some ways of describing it, but the important thing that it is an algebra which satisfies Jacobi. Good. So some of the things that you can compute with this, good. So these are kind of the plane waves that you have in the theory. You can extract your structure constant. So this is what you had in flat space. So these are the ones that Donald found a long time ago. So you see the structure constants for this guy are not really constants. Well, that's why I put constants like this. They're really momentum dependent. And now the ones for the modified Poisson, they're again just minimally modified by this factor 1 over u minus v, which is basically the z direction. Then you can construct 3-point correlators, and this is in terms of the structure constants. So again, for young mills, you can double copy them to gravity. You have this nice mixing here if you wish. We have done some higher orders. I will talk about the higher orders. You have the cyclic, you have again the Jacobi that just follows from the one I showed you before. Because it's work in progress, I won't show you precisely, but hopefully in a few weeks, in a couple of months maybe, we have, you never know. But we have
recorded here.
Sorry?
Everything is recorded, so be careful.
Ooh, not promising, but yeah, no. So these young people that I was promoting at the beginning, in particular Chandra and Kajal, they've done some excellent calculations. I think we've gone up to 4th or 5th order, and the nice thing is that indeed it behaves like a toy model. Like you can see how much, obviously it's a scalar theory, how much more easily you can compute things in it. And we can see some double copy relations as well at the level of the integrands for these correlators. Another thing that we're looking at that's really interesting is taking the soft limits for these correlators. They're a little bit different from what you have in flat space, but you have some very interesting symmetries here that I didn't have time to talk about. But because, as I was mentioning before, this toy model, the self-dual sector is integrable. We actually have an infinite set of symmetries. So we expect some infinite set of asymptotic symmetries probably in this case as well, and the various soft limits that follow from it. So this is the integrability part. So these are things that we're working on actively. These are more for the future. So one thing is the connection to ADS CFT. So now we have an ADS theory that's very, very simple. What would be the CFT dual? How to get, as I was showing before, you have this perturbation expansion. How can you get the full theory? What are the subtleties? There are some subtleties relative to the flat space case on how to go away from this toy model towards the full theory. So how much longer do I have?
Essentially 10 minutes.
Okay, good. So because I'll jump to a slightly different topic, unless there's any questions on this. Good. So I just wanted to quickly Good. So because I was highlighting this perturbation scheme, I wanted to very quickly go back to doing this other one, but the more standard one. And essentially, this is some recent work with Cuya, where we are not doing the self-dual now, we're doing the full theory, but in the linearized approximation. Now, if you work in the linearized approximation, this is some work I've done quite some years ago, it turns out that you can construct arbitrary gravity fluctuations from arbitrary Young-Mills fluctuations. So you can really set up your double copy in a very, very general way. It helps to work in this BRST formulation. There's a lot of benefits to it that I won't go into because of lack of time. But just a quick, hopefully everyone has seen the BRST formulation. So here, just a quick kind of reminder, you have the standard Lagrangian, you have your gauge fixing term, the ghost. The only thing I wanted to highlight is that for doing the double copy, in this case, we couple some sources to the ghosts. And then you can write some very nice dictionaries at linearized level. So this is just for the minimal thing where I'm just doing Young-Mills double copied with itself. I get my graviton fluctuation, my 2-form, my dilaton. Now this is really just linearized, unlike in the previous case. I have to do it via this bi-adjoint scalar. And the main feature here is that the way I put things together is via this convolution integral. And basically this just comes from the fact that in amplitudes, we're multiplying things at the same point in momentum space. Therefore, by the time you get to position space, you have this kind of this integral. An important rule that we found nice was this Leibniz rule, is that I can pull out derivatives, because this, I think someone was asking this question yesterday. Now, if I do a gauge transformation on this one, you can convince yourself that it leads to a linearized diffeo on these fields. And you can get also parameter dictionaries and source dictionaries, etc. Now, this is just at linearized level. I wanted to highlight, in case some people are curious, I won't have time to cover it now, but I'm happy to discuss on this. Like, you can go to higher orders in constructing these fields and gauge transformations using these homotopy algebra formulations. The sort of downside here is that we don't know how to construct specific solutions. So this is a more abstract formulations where we know how to recover like the functional form of equations of motions or symmetry transformations, but not specific solutions. But we are sort of thinking about it because this is ultimately a generalization of BRST and BV. But now very quickly in the last 5 minutes to kind of show you what we've managed to do on the sitter, just going back to the linearized case. So the main difficulty here is that the symmetries didn't really seem to want to work initially, because now I'm in a curved background. So my linearized fluctuation transforms like this with some nablas depending on the curved background. Whereas the gauge field, of course, still transforms the same way because this is just a scalar. But so we haven't managed to resolve this difficulty in general, but we have restricted to a gauge where it works. So this was the difficulty. Again, and we were working in the sitter, again, with this conformal looking metric. And we noticed that if I look at the sort of covariant derivatives, they are of this form. So if you go to temporal gauge, which for people who work in the sitter is a very, very standard choice, it turns out that things, for the symmetries at least, they collapse to kind of the same form as you have in flat space. Good. And then the other thing to do is generalize the convolution. So of course we had the standard one that came from Fourier transforming from momentum space. Now we're in the sitter. So now we have one direction that's different from the others, right? So we don't have the translation symmetry, but we have the rescaling. So the appropriate thing to do now is not a Fourier transform, but rather a Mellin transform. And this is the definition of the Mellin transforms, which you have to do along this eta direction. So along this direction in the sitter, this is the appropriate thing to do. And then the definition of the product of the convolution is this mixing between the standard one. So you see over the y coordinates, you can see the translation invariant, so 0 plus y, x minus y, and then over the theta, you can see the rescaling invariance. So you mix these two together. The point is that in Melian Fourier space, you get a local product. Now, so we define, this is how we define now our dictionary. And then we landed up on this dictionary. This is from our paper late last year. At linear level, we threw away the two forms, so we just focused on the symmetric part, and then we get some arbitrary constant parameters. So here to emphasize that this, in principle, this should work, you know, for any linearized solution, any configuration at linearized level. But we wanted to take a simple example. Oh, I forgot to mention, this also works for ADS via just a simple changing of the gauge fixing. So like I was saying in the beginning, de Sitter and anti-de Sitter kind of go together. But just to end, because I'm running out of time, as an example, we took, you know, what we usually take always the kind of simplest example that you can think of. So in Yang-Mills, we just took the point source solution. Now remember, I have to go to temporal gauge. It turns out that it looks something like this at linearized level. In gravity, we took the Sitter-Schwarzschild. Now I want to show you this first, because I guess this is what you are most likely to recognize as a Schwarzschild in a background with a cosmological constant. But we had to go to other coordinates, we had to linearize, and we had to go to temporal gauge. And we couldn't find this in the literature, so we did it ourselves, and at first we thought it looked really ugly, but then it kind of collapsed into this nice form, which I think looks a lot like these dipole things that Tanya was showing earlier. So probably in hindsight, if we'd known more about that stuff, we could have known earlier. But the point is that it collapses to a very nice form, and then indeed you can get it via this double copy and via a very simple form of the dictionary. So this was just to get it, and the dilaton vanishes quite straightforwardly. So we wanted to focus on just getting the pure gravity solution. And I think I had a picture there just to leave you, but I should end. So thank you.